So, hello again, everybody, and we will today cover two topics. One of them is spectrum bandwidth and how are we supposed to determine one. So, where we say that the spectrum starts here and ends here, and how we measure that. And the second one is the topic of filtering, digital filtering, which comes hand to hand to this bandwidth because it's actually a way for you to shape the spectrum of signal to match the specific bandwidth that you want to have. So if you recall, in practical exercise in one, I believe, we had some signal which I said I already filtered for you in advance somehow with some funny filter. I won't tell you which, yes, and so on and so on. But I promise that I'll tell you more about these filters and how they work in the process. So that's day is today. So let me actually start the pen. So we did discuss that spectrums are actually, in most cases, considered to be infinitely wide. Yes, like they do decay fast. So if we say, for example, for rectangular shaped signal like this, as we know from theory, spectrum has each of the odd numbered harmonics, and that continues all the way up to infinity. And the further you are away, the smaller and smaller these harmonics become. But they still contribute, they still give to the shape of this signal, and we have been able to confirm that by running some simulations and stuff like that. But in most practical areas, we actually want to say that, okay, we are going to cut it off here, like so. Yes, and basically what is going to happen to your signal. And more important is why would we want to cut off particularly here, or maybe not here, or maybe even here. Yes, so is there any logic, any reason as to where do we put this limit? So basically, yes, there is a reason, and the main reason is that we want to, on one hand, to, let's say, preserve as much energy as we can. Yes, but on the other hand, we don't want to overdo it to have to keep 1000, 2000, and so on of the harmonics. So we'll say that we want to preserve, let's say, I don't know, maybe 80% of the energy, where is the majority of the signal's energy focused, and say what is the bandwidth of that. Now, bandwidth, as of such, you probably already heard many times in terms of internet connection speed, in terms of communications and so on, like high broadband, high bandwidth connection. And that's true. In order to achieve higher data transmission rate, you do need more bandwidth. That means you need to use higher quality cables, later standards Wi-Fi or 5G networks, optical fiber, which all have high bandwidth. But that is more like a physical property of some medium, of some cable, of channel, because obviously you want your channel range of the frequencies in which it can operate to be as wide as possible so that you can put there a spectrum with bandwidth like so. Yes, and we know that if you make your pulses shorter and shorter, yes, then your spectrum becomes wider and wider. So they act in reverse. So you compress pulses, your spectrum becomes wider and requires you to use higher bandwidth channels. But at the same time, in telecommunications, as I was mentioning, for example, it's not really necessary to have this very accurate rectangular shape. We'll do fine with this one, which will preserve a lot of bandwidth. So actually, but will it have enough of energy? That's a question which we will cover today. So there are actually not one but two methods used to determine this limit. Where should we cut this bandwidth? One is called magnitude method, and it's using amplitude measurements. And another one is energy method, which, as it states from name, uses energy. Now, let's take them one by one, but before that, see some example. That here we have two radio station signals. This can be literally like any kind of radio stations, like TV, mobile, and so on. it's though down converted to certain lower frequencies, but the idea is literally the same. So the question is, where do we see that this signal spectrum ends and this signal spectrum starts? Yes, because they kind of overlap a little bit. So we need to have a clear um, definition of what is considered a spectrum bandwidth. And there is actually, if we speak about magnitude 1, existing and widely used by engineers called some, let's say, 3 decibel bandwidth. Now, what that means is that the maximum value here and the smallest possible value which we still accept should differ not more than by 3 decibel. So that's the maximum acceptable difference. Yes, so 3 decibel here. And whenever we fall below that level, we consider the spectrum of the signal is no more. Now, decibel is a relative unit, it's logarithmical unit. So if we speak about how much that is in a linear scale, so this is a log 10 base, yes, then that matches approximately uh, 0.5. Yes, so you can say that signal's power, not power, but amplitude of the component is the half of its maximum possible value. Yes, so whenever we fall below half, then we say, okay, anything else is considered to be, kind of irrelevant. Yes, so same way happens here. And despite the fact that they originally had different level, yes, you can see that this one is here, this one is a little bit up here, but the relative difference where it falls off by 3 decibel is the same. Yes. Now decibel is calculated like follows. So 10 logarithms. These are by base 10 of the ratio of something. So say for example power 1 versus power 2. For example, power of the signal 1 versus power of signal 2, or power of the signal versus power of the noise. Or if we speak about some absolute measurements, like we measure just the power of radiated signal or just the power of acoustic wave, then relative to some reference unit like 1 watt, 1 milliwatt, and so forth and so forth. So why engineers use them? Well, that's because it's convenient for them, because same picture in normal scale would have you to compare points at the 10 to the power of minus 5 and the points at the 10 to the power of minus 10, which are very difficult to compare with each other because they, well, are too close to each other. And especially if you will have somewhere also point to compare 10 to the power of 2, then you will see just 10 to the power of 2, and there you will see around 0 all the others. So this actually allows you to see more dynamic range. Also, one more benefit is that whenever you act with some systems, and we'll speak about it today also, you have to kind of multiply the signal. So for example, you have some amplifier that increases the power of the signal by K. So here you have signal X input, here you have signal Y output. So signal Y output is calculated as K multiplied by X. Now this K may not be a constant number, it may be some function also, yes, which makes it even more difficult. In that case, if you were to convert them to logarithmical scale, this multiplication would be replaced by addition, which is, again, for engineers, easier to do in head without having to run some MATLAB and stuff like that, or by simple calculators on paper, yes? So again, that's the convenience matter. We can actually even use some equipment to do this measurement. See, you can press some buttons, specify this limit, and accordingly it is going to measure this bandwidth and tell you that the spectrum starts here, ends here, in the correspondence to 3 decibel level. You can also use 6 decibel level and vice versa. So not necessarily it has to be always exactly 3, but 3 decibel is very commonly used point. Now, if we speak about the idea of this method, then it's pretty simple and straightforward, yes? So let's say you have some spectrum. Let's maybe make red colored spectrum with multiple amplitude components. And you want to decide which you are going to keep and which you are going to say goodbye to, yes? So basically the idea is pretty simple. First of all, you need to find the maximum one. Well, usually the maximum is tending to be at lower frequencies than at higher. So here we have frequency, which increases as we go. Yes, so this is a maximum of xk. And we also need to agree on a certain percentage of this maximum. How much of ratio-wise of this maximum should we keep? Like 50%, 25%, 60, 75%, etc., etc., which we denote as A. Like, for example, 0.7 of the maximum. Then we draw the line, which is this threshold of A multiplied by maximum, and we only keep the components that are above this maximum. So basically, that means for us that this component is well above the maximum, so it stays. This component is well above, no, a little bit above the maximum, so it stays. Now this component is below, so it goes away, and it goes away. So the bandwidth, therefore, is calculated and measured by these components, and that is it. So pretty simple, and actually you will actually even try yourself with some specified parameters to measure this bandwidth by using one or two criteria, magnitude or energy. Now for energy method, this is working slightly differently. Yes, for energy method, we don't really care about specific harmonic itself, because spectrum might look like somehow like this, which is completely possible, like this harmonic, then this smaller harmonic, this larger harmonic, this smaller harmonic, this larger, and so forth. So if we skip at this point, then we lose a lot of energy. Now energy criterion actually works as an integral criteria, which considers not just separate harmonics, but their total contribution of the energy. So you now need to calculate the energy, which is the square of each harmonic. Now you basically say that you can calculate well, this matches to the certain signal, yes, for example, like this, for which we know how to calculate energy, power, and all that stuff. So let's say we speak about average power. Yes, you just measure the average power of the signal that you have. You use Fourier transform to calculate its spectrum. And now what you need to do is to say, okay, I care about 90% of this energy, of this power. So where should I put the limit in this spectrum so that I have this 90% of this original power and all the other infinite long components tend only to 10%. Well, so the idea is like this, yes? So here we have 90% of the power of the signal, which we can calculate from the signal as a time function, how it's oscillating in time, yes? Then you calculate the spectrum, and then basically it's as simple as that. You take first harmonics, check the power, take second harmonic, add it on top of this. Now you have power of two harmonics, check if you exceed 90%, and do so until, yes, until certain number k, where you see that, okay, now at this number k, I'm actually over 90%. I'm 90.2%, for example. So you see that here you should stop and you don't include next harmonic, yes? So as simple as that, you basically kind of add, add until you meet this criteria. Now, for some situations, this method is better. For some situations, the method of magnitudes is better. Yes, so basically it depends on the task. Now, the important property here, why is it possible to use this energy method? Yes, is very simple stuff that actually, if we do nothing about it, then the energy which you calculate for the signal samples, you can consider it as a points, yes, like so. And the energy which you calculate for its spectrum obviously has to be the same because we are speaking about the same signal. And as you know, the energy preservance principle states that it cannot go nowhere suddenly and it cannot appear out of nowhere also. Yes. So that can actually be even demonstrated. Let's actually try fast octaves. The demonstration that it is true. Now, in this case, however, we are speaking about deliberately cutting off part of the energy. Now, we cannot really calculate full energy based on spectrum. It's more difficult for us, although possible, but we can easily calculate that for power or for the time signal. So let's check, for example, signal 111111000 1111000. So if I plot this signal x, then it's looking somehow like these trapezoids, yes. Well, if we add more ones and zeros, it's going to start looking rectangular. But the idea is that its energy can be easily calculated as this area, yes, beneath this line. Mathematically, all that we need to do is to simply say, okay, I want to have summation of all the x squared. So I square each value, add them together, and I get number 10. So what I'm going to do now is to calculate the spectrum by using Fourier transform of this signal. Don't forget to normalize it with the length. And then I'm going to calculate square of each absolute value of this spectrum and add them together. Now, wait, maybe I shouldn't normalize it. Just a moment, sorry. Probably I shouldn't have normalized it. Okay, summation absolute value x squared. Well, now it's 20. So I have 20 of them. Now I don't get why it's... So no, if I now divide with this length here, it's going to work. But I'm still a little bit uncertain as to why it works like that. Yes, but the energy has to be same in if you calculate for time domain and frequency domain. Yes, you just have to be aware of certain normalization techniques, which honestly looks a little bit shady here. But I'll get to the point of this before our practical exercise so that it actually is justified properly. Yes, but the idea is nonetheless the same. Yes, because it's the same signal, which is obviously. So, okay. No, with that in mind, if we now say that we don't necessarily want to have cut off energy, because that's what we state here, that we say, okay, the real power and therefore also energy of the signal is some number, but we are completely fine to have, let's say, 90% out of this number. So we are kind of less or equal to that power. So that gives us Bessel's inequality. That's the formula. Yes, that states that after cutting off the spectrum, after calculating certain limited bandwidth, your energy or power is going to be limited a little bit, yes, compared to the original one. Now, however, if you consider all of the possible harmonics all the way up to infinity, then this power should actually match. Yes, and I can actually see it here. That here we have 1 versus n. We have 1 versus n for this one, for x small, and we don't have it for x large. Well, anyway, yes, in a physical sense, that means that the signal components, yes, have the same energy in total like the entire signal as a whole. Yes, that's thanks to the orthogonality of the sines and cosines here that we have selected during our discrete Fourier transform. Now, in more details, we'll do this in practical exercise in 2 weeks, yes, where you will be given task to filter signal and then estimate what's its bandwidth after you have done filtering. So let's go to the filtering part.